Hello Starbase engineers. I am Daniel Bernoulli. For the next several hours, I will speak to you in monotone about fluid dynamics. In fluid dynamics, my principle, Bernoulli's principle, states that for an inviscid flow of a non-conducting fluid, an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. The principle is named after myself, Daniel Bernoulli. I published it in my book Hydrodynamica in 1738. Perhaps you have read it already. My principle can be applied to various types of fluid flow, resulting in what is loosely denoted as Bernoulli's equation. Again, named after myself, Daniel Bernoulli. In fact, there are different forms of the Bernoulli equation for different types of flow. The simple form of Bernoulli's principle is valid for incompressible flows. For example, most liquid flows and gases moving at low Mach number. More advanced forms may in some cases be applied to compressible flows at higher Mach numbers. See the derivations of the Bernoulli equation. Bernoulli's principle can be derived from the principle of conservation of energy. This states that, in a steady flow, the sum of all forms of energy in a fluid along a streamline is the same at all points on that streamline. This requires that the sum of kinetic energy, potential energy and internal energy remains constant. Thus an increase in the speed of the fluid, implying an increase in both its dynamic pressure and kinetic energy, occurs with a simultaneous decrease in the sum of its static pressure, potential energy and internal energy. If the fluid is flowing out of a reservoir, the sum of all forms of energy is the same on all streamlines because in a reservoir the energy per unit volume, the sum of pressure and gravitational potential, Greek letter rho gh, is the same everywhere. Bernoulli's principle can also be derived directly from Newton's second law. If a small volume of fluid is flowing horizontally from a region of high pressure to a region of low pressure, then there is more pressure behind than in front. This gives a net force on the volume, accelerating it along the streamline. Fluid particles are subject only to pressure and their own weight. If a fluid is flowing horizontally and along a section of a streamline, where the speed increases, it can only be because the fluid on that section has moved from a region of higher pressure to a region of lower pressure. And if its speed decreases, it can only be because it has moved from a region of lower pressure to a region of higher pressure. Consequently, within a fluid flowing horizontally, the highest speed occurs where the pressure is lowest, and the lowest speed occurs where the pressure is highest. This has been a blast for me. I think I have a knack for working with children. Do you have any openings at Starbase? If I start working at Starbase, then Miss Hendrickson would become Bernoulli's principal, ha 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 ha.